In problem number 11 on page 175, they tell us that the average 8% candidates sitting for an examination are actually awarded merit. Now what you're going to find sometimes in these questions is they use kind of different phrasing than you're used to. If they're not awarded merit, they failed, and if they are awarded merit, we're going to say they passed. All right, so first question is, how many candidates in each group are not expected to be awarded merit? So you've got to be really careful in these questions because the wording is critical. You'll notice here that this shifts gears now to saying they are not expected to be awarded merit. When the original question started talking about the probability they gave us is them being awarded merit. So since there's only the two possibilities, it's easy to find the other one. So let's go ahead and do that. I'm going to start by making sure I'm clear about what I'm talking about. The Y is going to be the number of candidates that do not pass. And I'm going to write this as a binomial distribution. Giving 50 candidates, the probability of not passing is 0.92. Now, to find the expected number of people that do not pass, I'm going to do n times p, or 50 times 0.92, and get the number of 46 candidates are expected not to pass. Now, in part B, they say find the variance, but now it's about the people that do pass, the people with merits. So I'm going to say X is the number of candidates that pass, and its binomial distribution is with a probability of 0.08. The variance is n times p times 1 minus p, and so what I'm going to find out is the variance is going to be 3.68. And then in part C, it says find the probability that 3, 4, or 5 candidates in a group of 50 are awarded merits. So now we're talking about my X distribution, and X could equal 3 or 4 or 5. And again, the group is 50, so we know what our N is. And so all I've got to do now is find the probability of X equals 3, X equals 4, and X equals 5. And what I'm going to do is I'm going to write the formula using the formula and the combinations. I'm going to write all this information down. This is critical. This shows I understand the method. And then I'm going to use my calculator, and I'm going to enter in 3, 4, and 5, put in 50 and the probability of 0.08, and then I'm going to get my probabilities from here. And so now all I've got to do is copy them down, being careful to write at least 5 digits for each one, and then I'm going to add them up to find the total probability, and then when I round to 3 significant figures, I get 0.566. Now in part C2, what we're looking at is a little switch in gears. What we're happening now is we're talking about 3, 4, or 5 candidates in both of 2 groups of 50. So no longer am I talking about just one group, I'm talking about 2 groups. My N is now 2. I'm looking at 2 groups. And they want to know the probability that 3, 4, or 5 candidates have been passed. Well, I know that probability. I just figured out in C part 1. And so I've got to be careful to make sure I don't use the rounded one. And when I do this, you're going to notice that 2 choose 2, that's going to be 1. And then this 1 minus my probability to the 0 is going to be 1. So really all I'm doing is taking the probability from part 1 to the second power. And I'm going to get this answer here, which is 0.320 to 3 significant figures. All right, let's look at the next one. On page 182, number 5, it says let X be the number of times an normal die is rolled up into including the first roll, which a 6 is obtained. This is a geometric distribution. The probability of getting a 6 is 1/6. In order to find the expected value, it's going to be 1 over the probability of success, or 6. And now they want me to find the probability that X is greater than 6. That means what's the probability that the first success happens after 6 rolls. Now you got to remember these rules I've written over here on the side. And this one is going to be 5/6 to the 6th, which is equal to 0.334897, or 0.335 to 3 significant figures. All right, let's take a look at the next one. Problem number 6. We've got a biased four-sided die, and biased means it's not fair. The probability of getting a 1 is going to be different than getting a 3, a 5, or a 7. So each probability is proportional to its score. That means that the probability of a 3 is 3 times more likely than the probability of getting a 1. And we can use this, and we did this kind of thing when we were doing probability distributions. If I set this up like a probability distribution table, and I could possibly have a 1, 3, 5, or 7, well, if 1 is x, then 3 is 3x, and 5 is 5x, and 7 is 7x. And see, all I've got to do now is add up all the probabilities. They have to equal 1. And I find out that x is equal to 1 over 16, which is going to enable me to find the probability of each one of these sides of the die being rolled. Now, once I know that, I can find the expected number of times the die will be rolled for the first prime number is obtained. This is make sure the first prime number is a 2. 1's not prime. So we've got 3, 5, and 7 on our die that are prime, and we've got a 1 that's not prime. Now, it says the first one, so that means this is a geometric distribution, and the probability of it not being prime is 1 over 16. And the expected value, the mean, or mu, is going to be 1 over p, or 1 over 1/16, which is just the reciprocal of 1/16, is going to be 16. So that's part A. The expected number of times for a non-prime number is going to be 16. Now, the probability that the first prime number is obtained on the third roll, well, now the prime probability is 15 over 16. And I'm going to use the formula, p times 1 minus p to the r minus 1. This is my success, and this is my failure, and the failure happened twice, and then the third time was a success. So now all I'm going to do is type that in my calculator and find out that the probability is going to be 15 over 4096. Now, as a decimal, it's going to be written like this. And you see -3 to the 10 to the -3. Just put 0, 0. Always one less 0 to the negative power. It's going to be 0.00366.2109 or 0.00366. Now remember, these zeros at the decimal point are not significant. So the three significant figures are going to be 0.00366. Okay, let's take a look at the next one. In number 7, Sylvie and Thierry are members of a choir. The probabilities that they can sing a perfect high C note on each attempt are 4/7 and 5/8. So let's write down our probabilities. And then who's expected to fail fewer times, and then we find the probability that both Thierry, okay, so I'm going to need to know both of these probabilities. All right, let's write that down. Let's see. The probability of failure for Sylvie is going to be 3/7, and then the probability of failure for Thierry is going to be 3/8. All right, let's go back to A. Failing fewer times before they sing a high note. Remember, in a geometric sequence, we're finding the probability, we're finding the first success. So the expected value of S in a geometric distribution is the first time they're successful. In this case, first time she sings a high note. And that's going to be 1 over P, or 7/4, or 1.75. And then the expected value for Thierry is that she has her first success on the 1.66th try. Now, though tries have to be integers, the expected value for Thierry is lower, so that means she's expected to have her success earlier than Sylvie. So that means that we expect her to fail fewer times than Sylvie. All right. B. Find the probability that both Sylvie and Thierry succeed in singing a high note on their second attempt. All right, so this is the probability that Sylvie and Thierry equal 2. S and T both have to equal 2. So the probability for Sylvie hitting it on the second try is the probability of success times probability of failure times 2 minus 1. And then Thierry's is 5/8 times 3/8 to the first power. Okay, we have 3/8 as a failure and 5/8 as a success. When you multiply both of those together, because they both have to happen, we get 0.057399. Remember, when we're rounding to 3 significant figures, that first 0 after the decimal point doesn't count, and so it's going to be 0.0574. And then I just want to quickly remind you, these are the formulas that you need to remember. The top one for the geometric is going to be given to you, but these bottom two you're going to need to memorize. All right, let's take a look at the next one.